Welcome back. In this video, I'm going to be showing you a few more tests that we can use to determine if an infinite series converges or diverges. But first, I want to talk to you about the harmonic series. Now, the harmonic series is the sum of 1 over n, which is 1 plus a half plus a third plus a fourth plus a fifth and a sixth and a seventh and so on. Okay, that's the harmonic series. I'm telling you right now the harmonic series diverges. And in this video, I'm going to prove that to you two different ways. I'm going to start by just, trying to reason with you. Okay, so S is going to be the harmonic series. 1 plus a half plus a third plus fourth plus fifth and a sixth and a seventh and so on. Okay, but R, I'm going to introduce this other series. R is 1 plus a half plus 2 fourths, 4 eighths, and if this kept going on, I would have 8 sixteenths, which would go up until S was 1 over 16. And then when S went 1 over 17, R would be 1 over 32, all the way until S was 1 over 32. Okay, so the pattern here is that I'm just going to block off some stuff in red, and maybe that ends over here somewhere. But then there will be another one, right? And there will always be these red brackets that I can combine to add up to a half. So R is also equivalent to 1 plus a half plus a half plus a half plus a half, and so on. Okay? Meaning that R is pretty clearly going to diverge. Okay? Okay? Which is to say that the R adds up and it gets arbitrarily large. It goes to infinity. Okay? But now I'm going to propose that S is even bigger than R, right? Because if I got rid of these red brackets kind of just in my way, and I directly compared a third to a fourth, a third is bigger. Okay? If I compare a fifth to an eighth, a fifth is bigger. A sixth is bigger than an eighth, and a seventh is bigger than an eighth. Okay, so S is definitely bigger than R. Okay, as a result, I'm going to conclude, since S is bigger than R and R goes to infinity, S has to be even bigger than infinity, which means S is going to infinity as well. So I'm going to say S also diverges. Okay, and S is the harmonic series. So this is the first reason I'm showing you that the harmonic series diverges. A technique that I just used where I said, hey, this is even bigger than infinity, so it must also be infinity, that's called direct comparison. So the theorem is if we've got a convergent series, and I'm assuming positive terms, or like the absolute value of Bn is less than the absolute value of An, the terms are smaller, then the sum of the smaller terms is also going to converge. So to translate that into English, I would say something like smaller than the convergent series is going to be a convergent series. And then looking at the second statement, if the sum of An diverges and the terms of Bn are even bigger than the terms of An, well, then Bn is going to diverge as well. And I think, yeah, as it's written, this is assuming a series of positive numbers. Okay, and we'll talk about alternating series next time. Okay, but this would be equivalent to saying that bigger than a divergent series equals divergent, right? Or bigger than infinity is infinity. And while in AP Calculus, the principle of direct comparison is really most commonly tested in multiple choice on kind of a conceptual level, I want to show you how this works. Okay, so let's look at the sum of 1 over the square root of n and show that it diverges by comparison with the harmonic series, which we already know diverges. All right, so I'm going to just say, all right, let H be the harmonic series. H is 1 over 1 plus. Okay, that should be enough. And then I'm going to say, maybe for comparison, let's look at S, which is 1 over the square root of n. So 1 over the square root of 1 plus 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4, and so on. Okay. Well, we know, in general, that the square root of n is less than n as long as n is greater than 1. Okay? Which is saying that 1 over the square root of n is greater than 1 over n. That might be a fact that they didn't tell you about in algebra class, that if you flip both sides of an inequality, it reverses the direction. But if you think about it, it's true, because 3 is greater than 2, but 1/3 is less than 1/2. Okay, throw that out there. Okay, but I'm seeing now that the terms of S are bigger than the terms of H. right? So S is greater than H, and I know that H goes to infinity, so therefore S also goes to infinity. Okay? Let's use the direct comparison principle to show that a series converges. Okay, this one we're going to want to show it converges, but we have to think of something that we know converges already, and that would be from the last lesson, the sum of 1 over 2 to the n. Okay, so I'm going to write out the terms of 1 over 2 to the n, or actually maybe I won't. Okay, I think I'm going to approach this a different way. I'm going to say that if n is a positive number, which it is if n is running from 0 to infinity, I've got 2 to the n plus n always bigger than 2 to the n. Right? Because you add a positive number to a quantity and it gets bigger. Okay, we know that. We've known that for a long time. Okay, therefore, 1 over 2 to the n plus n is less than 1 over 2 to the n when n is greater than 0. So the sum of 1 over 2 to the n plus n is less than the sum of 1 over 2 to the n. And this is 0 to infinity. We've got a formula for this. This is a geometric series. Okay, first term would be 1 times 1 over 1 minus a half. That will end up being 2. So I know that since the sum of 1 over 2 to the n plus n is less than 2, it has to converge. But again, this is most likely going to be tested as a multiple choice item on a conceptual level. Now I want to tell you about the integral test. And, well, the reason I told you about direct comparison before the integral test is that a person would need to use the principle of direct comparison to prove the integral test. Okay, and the integral test says that, if you've got a series of positive and decreasing terms, the function that defines them being continuous, you'll have convergence if and only if the corresponding improper integral converges, right? So it's really drawing the connection between this series and that integral. And what it's saying is that they'll either both converge or they'll both diverge. And I'm not going to prove this for you. I'm just going to do a couple of examples of it for you. If you're interested in the proof, I've got a video of it. In fact, you can probably click like right there and get taken to the proof of it. And it doesn't take that long. It's very visual. It's easy to understand, I think. And if you're curious, check that out. But if you just want to use the integral test, let's just get to it. Let's use the integral test on the harmonic series. Okay. So in order to use the integral test to show this, we're going to want to compare this to its corresponding improper integral. So the sum of 1 over n is going to be related to the integral from 1 to infinity, right? 1 to infinity. Okay, you just do the same bounds of 1 over x dx. Okay, we know an antiderivative for 1 over x. Okay, that's natural log of x, log of the absolute value of x. And we're interested in letting x run from 1 up to infinity. Okay, and we studied improper integrals in this class. We know that we can let an integral run all the way to infinity. We just take the limit of the antiderivative. So this is going to be the limit as x approaches of the log of x. I don't really need an absolute value because if x is going to infinity, well, it's definitely positive, minus the log of 1, right? And you think to yourself, what exponent would I have to put on e to get infinity? That's like the log of x as x approaches infinity. And well, there's no finite exponent I would put on e to get an infinite value. So I know that this limit doesn't exist or goes to infinity, therefore the harmonic series diverges. Because we showed that the corresponding improper integral diverged. Okay, now here's a couple for you to try on your own. Okay, I want you to try to run the integral test on these two series to determine whether they converge or diverge. And I'll start you off with a quick hint. You're going to want to compute these two integrals. Okay, so have at it. You're going to want to pause the video, and then work it on your own, and then start it up because the answers are just going to pop up in a couple seconds. All right, there you go. So I start by rewriting it as a power, right? We always want to look at a fraction and rewrite it as a power of x if that's possible. I use the power rule to anti-differentiate. I ran the limit, and I found, okay, over here, the improper integral was a finite value, therefore the corresponding series converged. And then on the right side, when I anti-differentiated, really what happened was the power in the denominator was not big enough to where when I bumped it up by 1 for the power rule, it stayed in the denominator, and so I ended up having infinity in the numerator, causing my limit to non-exist, causing my sum to diverge. Okay? And maybe you noticed that it has to do with a power when we apply the power rule that's determining whether or not these things are converging. That idea is called the p-series test. And so I'm just going to tell it to you that the sum of 1 over n to a power converges if and only if that power in the denominator is greater than 1. Okay? And you can prove this yourself using the integral test. So let's do a couple quick examples. All right, this one, n times the 5th root of n in the denominator, I can rewrite that as 1 over n to the 6/5, right, because it's 1 plus a 5th. And I'm going to say this converges by the p-series test p is equal to 6/5, which is greater than 1. Okay? But then this one over here, I'm going to say, well, this is the sum of 1 over n to the 2/5 power, right? Because the 5th root is the 1/5 power. Okay, and I'm going to say that diverges by the p-series test. P is equal to 2/5, which is less than or equal to 1, which would mean that the series was going to diverge. And then I'm just going to point out that this is not a p-series, so we're not going to be able to use the p-series test on it. It just has to be n to a power in the denominator. No addition, no other stuff going on. So we need something else for that series. So the last test I've got for you is called the limit comparison test. And it basically works like if you've got a series in mind that you know converges or diverges, and you can show that the limit of the ratio of your series to the series you're interested in is positive and finite, then they'll have the same convergence or divergence behavior. But like the reverse of this does not hold. If the limit is not positive and finite, no conclusion can be drawn. We can't say that, they have the opposite behavior. If we could say that, we wouldn't need any other tests. So let's work a couple of examples, right? This one is bigger on bottom, but the first one is bigger on bottom by 2, so I'm going to limit compare with 1 over n squared. So I'm going to start by saying the sum from 1 to infinity of 1 over n squared converges by the p-series test. P is equal to 2, which is greater than 1. Okay? Then I compute the limit of the ratio of the terms. The limit as n approaches infinity of 1 over n squared minus 3n plus 1 divided by 1 over n squared, but that's not going to be the way to go algebraically. We're going to multiply that by n squared over 1. This is the same thing. And then I'm going to see that if I was to combine these, I'd have n squared in the top and n squared in the bottom. And that limit, is the ratio of the leading coefficients of the biggest thing, and it's going to be 1. And I'll tell you, you need to have that, essentially the same, so you're going to divide the coefficients thing happening with your limit every time, or else you're doing the limit comparison test wrong. Okay, so I'm going to say that that limit is positive and finite. And I'm going to conclude that this thing does the same as 1 over n squared. So the sum from 1 to infinity of 1 over n squared minus 3n plus 1 also converges. Okay. And then I'm going to scroll down a little bit and look at this one. Okay. N squared plus 2n over n to the 3 plus 1, that's bigger on bottom by 1. So I'm going to say the sum of 1 over n for comparison. Okay, we know that diverges because it's the harmonic series. You could say it's the p-series test, but everyone's just going to accept that the harmonic series diverges. Okay, then I'm going to compute the limit of the ratio. Okay, so n squared plus 2n divided by n to the 3 plus 1 multiplied by n over 1 is like divided by 1 over n, and that's going to, again, be n to the 3 plus 2n squared over n to the 3 plus 1. That limit's going to be 1 over 1. That's positive and finite. Got enough room? Yeah. Okay. Therefore, this series does the exact same thing as the harmonic series, which is to say it also diverges. Okay. I'm going to show you a couple more for you to try on your own. So you should try these. I'll say you just think about the difference in the powers of the top and bottom. And so you should pause, try to work through them, check your work against mine. Okay, there you go. This one I compared to 1 over n to the 2/3. I'm realizing the one on the bottom is very similar to one I did earlier that was bigger on bottom by 2 powers, so I'm just going to tell you, you could compare that with 1 over n squared, and you would show that it converged. But, that's going to be all of the comparison tests and all the examples I got for this video, so I'm just going to tell you, thanks for watching.